All right. Hey everyone. My name is Carter. I'm an assistant professor in the computer science and engineering department. And since the next speaker is someone who I invited, I feel obligated to give him at least a little bit of an introduction. So David is visiting us from Georgia Tech, where he does research on digital forensics for machine learning. We've been friends for many years now. We overlapped by 2 years back when I was a PhD student. So yeah, without further ado, please join me in welcoming David.
So a very important thing with AI systems is that when they fail, we're able to investigate them. So that is what my entire presentation is. So aside from the previous talks, this one will be specifically about how to research. So specifically looking at the issue reads explainability. Before I get into that, just a little research review of what I've done. So primarily, I do forensics of AI systems. I have qualifications in security, NC6, and I have short I've also identified and mitigated next generation AI threats. I've all over TCS, PSS, and Attribution, and IPSB. Aside from that, I've done kind of tangential work on proactive cybercrime mitigation, which is involved detecting click fraud and something of that nature. But overall, underpinning my research is kind of forensic investigation of AI systems and kind of connecting program analysis with AI security. So let's start off with an investigation from the forensic investigator perspective on the self-directed car going to identify a sign. So the self-directed car is going, it sees a merge sign. Merge sign is inconspicuous looking, but has a visual action on it. So this car is using the sign recognition model to make all its decisions. Fortunately, the driver, who's probably asleep, doesn't recognize that the attackers have actually affected the model such that the attackers have affected the model such that when it sees this particular sign, it will misclassify it, and it will ultimately cause the car to crash. So thankfully, we have our investigator, Pico, comes in, saving the day, and his primary suspect is the sign recognition model because we all know that these kind of models are prone to adversarial examples. They're prone to data poisoning attacks on the back doors, and many other things that definitely don't have time to get into. So it's going to use the standard deep learning model vetting tools, which honestly apply machine learning or advanced image processing map to detect whether the model has been tampered. So he's going to take the sign recognition model, apply these tools, and hopefully determine that there was a sign, there's a patch in the back door on the sign that caused the car to fail. Unfortunately, there are some problems with this approach. The first problem is that these tools all assume model access. So in the wild, when you have this car crashing, you might not have, the forensic investigator might not be able to go in and pick up that model for investigation. It could be encrypted, it could just be straight up inaccessible. The company might not want to cooperate and give you that model. Things like the self-driving car can also employ online learning. So online learning is the process where the weights model get updated over time. So it makes the in-field representation of the model different from the model that may have been at the Tesla station. So this raises the question of, if we don't have unique weights of the car, how do we actually investigate that it failed? So theoretically, if those two things were an issue and we were able to cover both the model and the unique car weights, what do we do? How do we test it? So these tools all require some sort of instrumentable model, so we want to set them up in some sort of like source code level testing place, right? And apply the existing white box tools to be able to test them. But if we don't have, we just have an in-memory representation. So if we recover the weights and want to test them, we don't have to do testing. So this is where my work came in, which is AI psychiatry forensic investigation of networks and memory images. So taking the self-driving car example, we would extract the memory, the CPU memory from the self-driving car, and this would be given input as first what the system does is how do we get the model of the car? Well, first, the system identifies the model via its directed acyclic graph structure and identifies all the able to identify the layers and correctly basic the graph structure, there's a problem. And the problem is these tensors might not be accessible via direct linear traversal from the layers. And it's kind of like it's dependent on the framework in where how this actually happens. But our approach takes kind of an agnostic recovery approach, which uses feedback driven from the previous step to recover all the weights that emanate to the machine learning system. So now that we've recovered all the weights and layers, how do we actually use the model? So we have to set up some sort of base environment, but we've thankfully identified the model at this point. So we can set up that model in that test environment with empty weights and layers, and we host and map them back into a testing environment. So this entire process outputs some sort of investigatable model where now people can correctly use data to test and find back. We evaluated our system across 30 different models and deployed across PyTorch and TensorFlow. So these models range from object detection models to smaller language models to classification models. And we can first see that, well, we trained these on Lisa 10 MQB, and the input to aid all these scenarios was the CPU and GPU memory extracted when we deployed the model. So we can first see that we've recovered up to 94 million weights with 100% accuracy. I know this number of weights is small relative to today, but back when this research was going on, 94 million was a decent amount. Research recovered more, but it doesn't really matter. Anyways, all models were deployed on GPU and were correctly recovered. We recovered as many as 9 GPU templates, as close to 11 GPU templates. Models from multiple application domains were recovered. So, like I said, object detection model. That was really loud. And a smaller language model. Yeah. So now that we've actually recovered the model, we want to be able to test it. And to demonstrate that our testing was successful, we want to show that the deployed accuracy was the same as the rehosted accuracy. If we show that, then we can reasonably say, okay, our tested model had the same performance as the deployed one, so we've correctly recovered. You can also see the number of layer types was the same across each framework, which makes sense because this tool is framework agnostic. And that's it for this paper. So in the paper, we're also going to forensics of online learning and the investigation of more backward models and a case study of that. And then we compare this to black box approaches. So approaches where, let's say the investigator could not get access to the model, how would they test it and how does it compare to our ape-enabled approach? So let's go to another.
I'll move back one more real quick.
Yeah.
I was gonna take a picture of that real quick. Thanks. Appreciate it. Thank you.
Any questions so far?
The recovery of the memory of the GPU and CPU, how did you retain the state of those components?
That's kind of, that's a bit orthogonal. We assume that it was, the system's still running.
Okay.
Or let's say we have a drone or something like that, we can turn the drone on, right? And extract the memory via some existing ID to start. So,
Gotcha.
yeah. Any other? So let's go to another self-driving car investigation where in this case it's a bit more complicated. So we have the same merge sign, except this time we have a proprietary sign recognition model. So remember that in all of our tested cases, we use existing models that might be very commonly used, right? But this might not always be the case. But let's say that the backdoor attack happened in this scenario. Car crashes. Our one crashes.
A little too close to home there. Oh, you're talking about a fact, huh? You got the point.
Now we get the AI investigation. That's not.
That was so well timed.
Copilot got nervous.
Check because of the rescue again, but this time it's a bit harder because the proprietary proprietary sign recognition model is essentially an existing state-of-the-art model, but has been improved by whatever company is using it to utilize other layers or any other techniques they want to incorporate into that existing model. So here, there's some new challenges that come up. So first, we might want to use A to recover the model weights and apply some sort of white box testing techniques. However, this requires code instrumentation. So like I said before, we were able to set up that model in that testing environment and plug the tensors back in. But this is kind of hard to do if you don't know what the model actually is or if the layer type is completely unknown. So like I said, it requires a testing model setup at the source code level, but not having the source code is hard, especially when all the layers are custom. So if we use H recovered in the layer types, but unfortunately the layers were unknown, this step would fail, right? And that would mean that we wouldn't be able to get the testing model set up, we wouldn't be able to instrument the code, white box techniques, and we wouldn't be able to apply white box techniques. So based on that, we have to create a new system called Zen, which combines PL model representations for attribution and reuse. So this takes the same inputs, the CPU and GPU memory, and we apply the same approach for weight recovery. The weights are still in memory, there's nothing special about that. We also recover the code of the process this time. We isolate the model specific code. So this might be the byte code of each of the layers, or this might be, the byte code of each of the layers. We get a model fingerprint. So this fingerprint is constructed based on the model specific code instrumentation as well as the structure of the model. So its layers, its connections, its graph structure, and so on. We've pre-built a base model library containing the common state-of-the-art models. So in this case, this is just two examples. But let's say we have a YOLO V5 model or a Palm 3 model, whatever. We know that it has, I'm blocking my view there, but the mathematical structure has a specific typical number of weights, change, the topology, the layer types, and so on, right? And then from the code side, there's classes, functions, and a whole bunch of other things that these systems use that we also consider in our forensics. So what we do is we take that model's fingerprint, compare it to the base model library, and do some sort of attribution. So can we figure out where that model originated from? Once we figure out where the model originated from, we now have like a base from where we can find all the differences. So from there, once we identify all the differences, we can construct patches, instantiate the model, and do the same sort of testing. This isn't a complete pipeline. If you want to find that, I can send you the paper, or we can talk about it after. So in our experiment setup, we had 21 models deployed. In the previous case, we had 30, but those were less variety and more depth across frameworks and posing types. Here we have a larger variety. We used 7 model families for which we generated, we found forks, custom forks where these models were customized with new research or existed their own research that was in the process of getting published, right? So these new state-of-the-art models had great customization built on top of existing state-of-the-art models. So we deployed them, and we can see in this table that the deployed model, all the citations, you can see them all in the paper, but these are all models that are flowing better than the original base model. So we can see the 7 base models for each customized deployed model. And we can see that Zen correctly attributed each customized model to the correct base model, which is what we want to see. Then, once we attributed the model to the base model, we want to find all the changes. So what functions were modified, what classes were added, and what the overall change percent is. We can see that upwards of 406 functions could be modified, and Zen can still correctly generate a number of patches needed for reuse. And as much of the code base, 83.3% was changed, and it still works. So we measure the post-patching performance. We measure Zen's performance the same way that we did 8, and we show that the deployment performance matches Zen's testing performance. And we can see that they all match, which means that our application of Zen was successful. And there's much more in the paper. Copyright investigation.
Are you using the term patch to mean the difference between the base model and whatever changes they?
Yeah, so we find the base model and we construct a patch such that when we set up the base model in a testing environment, we can directly apply the patching of the changes that we made to that base model to kind of replicate the behavior.
So it's just a carbon copy of the found source code, or recovered source code, I guess?
Well, you don't have the source code, right?
Right, but
Yeah.
you have the bits.
Essentially, you're trying to find the copy, yes, you're trying to get the copy of the model, right?
Okay.
But yeah, we have potential evasions and defense strategies for, attribution. And then we also have a detailed comparison to prior work why this is necessary. Yeah, that's.
I have a quick question. So how do you interrogate memory? Is this something you have access to?
We built a plugin on volatility, so all our code is built on volatility.
So I'm sorry, so you don't have access and you want to try and recover what the type of neural net it is and all its weights. And you're doing it by, I don't know what volatility does, it puts a lot of inputs in, or you're inspecting.
So volatility is just the framework that lets you interrogate the memory, right? I can look at data structures in memory, recover data structures, and so on. This is entirely program analysis and kind of binary analysis based work, right? So we're not doing any AI techniques here. We're solely trying to get the AI model out of the system so that we can investigate.
By interrogating
The
the memory of.
Yeah.
Running the state memory of the running system.
Running. Okay. I didn't understand, thank you.
Yeah, of course.
So did I read that right? That basically you're saying Zen could reestablish and correctly attribute the model back to it from based on your original model foundation, even though there have been 83% changes?
Yes, there's a caveat. That's a smaller model, right? So in that case, it was like mobile net compared to some customized mobile net. When the code base is smaller, the changes are larger, right?
Makes sense.
So, but if we had like a giant system where it's like ChatGPT, completely modified, we can't test that. We don't have access to ChatGPT's foundation model or whatever, but I'm assuming it would be different. We did observe though that in the bigger models that we had, so like the old models, the percent change was different, right? It was much lower, right? And even though the number of functions added, or classes added, or whatever was high, right? And that's just because the code base is so much larger.
I find that any of the vendors are doing any kind of anti-forensic or obfuscation or that kind of thing to protect their intellectual property.
I haven't found anything showing that.
Can you say more about how you're fingerprinting the models?
Yeah, so the models have essentially a graph structure. So once we get that graph structure, we can get the layer shapes, get the connection between everything. That kind of serves as a component of the figure, right? And the remaining piece of the component is all code. So kind of how the functions looking, what are their inputs, arguments, what is there, right? What classes are in memory, so on. And all right, thank you guys.
Thank you.